Avi Loeb, a well-known astrophysicist noted for his unconventional yet thought-provoking views on extraterrestrial life and interstellar phenomena, recently turned his attention to the mysterious object designated 3I/Atlas. This object, which entered our solar system from interstellar space, has attracted considerable interest because it displays a number of unusual characteristics that distinguish it from previous interstellar visitors. One of the most important clues Loeb focused on is the object's non-gravitational acceleration. Under normal circumstances, celestial bodies, especially comets, follow trajectories entirely determined by gravity. However, 3I/Atlas exhibits a slight but measurable deviation from this purely gravitational path. Loeb calculated that the magnitude of this acceleration is less than 4.6 meters per day, a subtle push that cannot be explained by gravity alone. Such behavior is typically associated with cometary outgassing, a process in which volatile materials from a comet's surface vaporize when heated by the sun, causing jets of gas and dust that act as miniature thrusters. By carefully analyzing the relationship between the strength of the acceleration and the likely rate of mass loss caused by sublimation, Loeb was able to estimate the mass of the cometary nucleus itself. The number he arrived at was nothing short of remarkable. Based on the observed acceleration and reasonable assumptions about the rate at which the object is shedding mass, Loeb concluded that 3I/Atlas must possess a total mass exceeding 33 billion tons. To put this into perspective, that would imply a solid nucleus measuring more than 5 kilometers across. This is an extraordinarily large size for an interstellar comet, and one that sits at the very upper boundary of estimates derived from observations made using the Hubble Space Telescope. For comparison, the first known interstellar object, 1I/Oumuamua, was only about 400 meters in length, and even the second interstellar visitor, 2I/Borisov, was estimated to be around 1 kilometer in size. If Loeb's calculations are correct, 3I/Atlas dwarfs both of these earlier objects not just in diameter, but also in mass. In fact, it would be tens of thousands of times more massive than either of them, placing it in a completely different category of interstellar travelers. Its size alone makes it an extremely rare find, something far beyond what astronomers expected to encounter so soon after detecting the first two interstellar bodies. Loeb emphasizes that our current understanding of the distribution of heavy elements and solid bodies in the galaxy suggests that enormous interstellar objects of this scale should be exceedingly uncommon. By his reasoning, based on the typical processes that produce heavy elements in stars and subsequently distribute them into planetary systems, we would statistically need to detect around 100,000 objects similar in size to Oumuamua before encountering a single object as massive and large as 3I/Atlas. Yet strangely, astronomers have only identified 3 interstellar objects in total so far, and one of those appears to be this gigantic anomaly. This discrepancy highlights just how unusual and fortunate this discovery is. The presence of such a massive object entering our solar system raises fundamental questions about how typical or atypical the processes that form and eject material into interstellar space might actually be. It also prompts curiosity about what kinds of exotic environments or rare cosmic events could produce such a large body. Adding to the sense of mystery and opportunity is the flight path that 3I/Atlas is currently following. Unlike many comets that travel on wide, sweeping trajectories, this object is passing unusually close to the orbital paths of several planets in our solar system. Of particular interest is its upcoming encounter with Mars. According to current trajectory forecasts, 3I/Atlas is expected to pass by Mars at a distance of roughly 2.7 million kilometers, a remarkably close approach by interstellar standards. Such a near passage provides scientists with a unique observational advantage. Loeb argues that this is a rare and ideal moment to gather high-quality data, especially because one of the most powerful scientific cameras ever sent to another planet, the HiRISE camera aboard NASA's Mars Reconnaissance Orbiter, is perfectly positioned to capture detailed images of the comet. Loeb proposes that the HiRISE instrument should be aimed at 3I/Atlas during its flyby of Mars. HiRISE is capable of capturing incredibly high-resolution images, often revealing features as small as a meter across on the Martian surface. Although the comet will be far more distant than typical Martian targets, the camera's optics are still sensitive enough to detect brightness levels and variations that could reveal the true size of the comet's nucleus. By analyzing the amount of sunlight reflected from the object's core, astronomers would be able to estimate its total surface area and therefore determine whether it is indeed as large as Loeb's calculations suggest. This measurement would provide a much-needed confirmation or refutation of the claim that 3I/Atlas possesses an unusually massive nucleus. If the nucleus is conclusively shown to exceed 5 kilometers in diameter, then the interstellar origin of such a large body would become even more difficult to explain using conventional astrophysical models. Although 3I/Atlas is currently classified as a comet because of its visible outgassing and coma, Loeb does not dismiss the possibility of more exotic explanations. His previous research on objects such as Oumuamua has explored the idea that some interstellar objects could be artificial in origin, perhaps fragments or remnants of technological civilizations that predate humanity by millions or even billions of years. While he cautions that such ideas should not be adopted prematurely, he also stresses that they should not be ignored if the data becomes difficult to reconcile with natural explanations alone. If 3I/Atlas indeed turns out to be as massive as predicted, its formation would require conditions or processes that are extremely rare in the galaxy. Scientists would then need to consider alternative hypotheses, however unlikely at first glance, about its origin or purpose. Loeb advises that the chemical composition of the comet's surface is not enough to rule out unconventional possibilities, because even an artificial object could accumulate natural cosmic dust and ice over long periods of drifting through interstellar space. Just as one cannot judge a book solely by its cover, he argues, one cannot determine the true nature of an interstellar object based only on surface characteristics. What makes this developing situation even more intriguing is the timeline of upcoming observations. Over the next several weeks and months, 3I/Atlas will move through regions of the solar system that allow astronomers to observe it from multiple vantage points. Ground-based telescopes, space telescopes, and planetary orbiters, such as those around Mars, will all have opportunities to collect data. These observations will reveal vital information about the object's rotation, composition, mass distribution, and physical structure. If its trajectory continues to show anomalous acceleration, or if its brightness varies in unexpected patterns, scientists may need to reassess their assumptions about what types of objects populate interstellar space. Loeb maintains that science progresses most effectively when unusual data encourages researchers to question established models rather than forcing the data to fit preconceived expectations. Ultimately, 3I/Atlas represents much more than just another comet passing through our solar system. Whether it is a naturally occurring giant forged in the depths of a distant planetary system, a rare fragment ejected by a cosmic catastrophe, or something far more unusual, its arrival offers a rare chance to deepen our understanding of the universe. The enormous scale of the object, combined with its precise trajectory and close approach to Mars, makes it a cosmic gift of sorts, a once-in-generations opportunity to study an interstellar visitor up close. For astronomers, planetary scientists, and researchers studying the origins of cosmic materials, 3I/Atlas may hold answers to long-standing questions about how the galaxy forms and circulates solid bodies across vast distances. For those more open to speculative or unconventional ideas, it may serve as a reminder that the universe still contains mysteries far beyond our current understanding, and that each new discovery has the potential to reshape our view of what is possible. As Loeb suggests, patience and careful observation will determine what kind of object 3I/Atlas truly is. Over time, as multiple instruments gather more precise measurements, scientists will gain a clearer picture of its mass, structure, and origin. Whether it proves to be simply an extraordinarily massive comet or something more enigmatic, Its passage through our solar system marks an extraordinary moment in modern astronomy. Until those answers arrive, the scientific community, and indeed the public at large, can only watch with anticipation, aware that this rare interstellar traveler may well redefine parts of our understanding of the cosmos.